Alright, let's go ahead and run the little Dijkstra's algorithm, right, on this particular thing. And yeah, it'll be quite a fun little experience, right? So Dijkstra's is a greedy algorithm where essentially the idea is that you are trying to pick uh, you are trying to make the greediest choices possible. Now what is greedy here? Greedy essentially means that you are trying to get from a particular vertex to any other vertex, right? It doesn't find necessarily all pair shortest path, but it finds shortest path from one particular source to basically all other vertices in the graph, right? That is what it does. So let's get started. So we'll make a couple of things here. So we'll write the name of the node here, right? So that can be a particular column, right? So we will have that. Then we will also have a vertex called visited, or sorry, not vertex, just a column called visited. I am not writing the whole word because the idea is understood. And then we will just add another column called cost. Okay, now the cost one I'm not going to bound, it will basically grow quite a lot. Now you will start from A. Okay, let's just start from A. Okay, so what happens essentially, now the moment when we step into A, we say that we have visited it. That's it. Okay, it is visited, and the cost from A to A is essentially 0. Like we don't even write it, we just put a hyphen dash whatever, but yeah, 0 is essentially the cost. The cost to everything else right now is infinity, right? So I'm going to just kind of no, there is no need to write it, it'll become quite messy, right? So yeah, anyways, immediately it notices that okay, the vertices that I have near me are B and F, right? So B and F, and I will also actually add another column. I just forgot about that. Let me just put it here, and I will say from, right? From which vertex am I coming to a particular point? That is basically the idea. So to get to A, of course we don't have to take any from. A is in fact A, so there is no need to travel or go anywhere in the universe, right? So that is basically it. Now the cost from A to B is in fact 7, right? That is what we find out initially. And the cost from A to F is 11, right? That is what we find out initially. That is our initial understanding, which is completely fine. It can be wrong, but that is possible. Next, what happens is it picks, so it eliminates things that are in the visited list, and it looks at the things that are not visited. So B and F, which one has the lowest cost? So 7, so B clearly has the cheapest cost, so it will go to B and it will mark it as visited. Okay, then it will say okay, what are the neighbors for B? So the neighbors for B are BD and BC. So D and C are essentially added to this list, and it says now that to get to D it will cost us 11. Okay, but remember that to get to B it costs us a 7. So 7 plus 11 is essentially what the cost is, right? So we will say that the cost to reach a D is in fact 18 from B, because everything we write here is with respect to A. It is our node where we have started everything from. That is the reason why the cost is essentially written in this kind of a fashion. We are trying to say that this is how much it will cost to actually reach a particular point. Okay, now see, so BC will cost us 12, but again A to B costs 7, so 7 plus 12 will become a 19, and we are getting to C from B, so we will have to reflect that as well. Okay, and therefore we can move on from B and we can move to the next cheapest possible vertex, which is F, right? So now we go to F. The cost of F from A is 11. So at F we notice that we can get to E and G. Those are the two edges that we can explore essentially, right? So E and G, right? Can I expand the lines? Is there any room to do that? I guess there is, but it looks a bit wonky. This serves the purpose. I guess that is more than enough. Yeah, okay, alright. So now we go to F, right? So yeah, G and D were explored, or not explored rather, they were just noted down as sort of neighbors of F. Now F says, F to E costs us a 10, but you have to also note that A to F costs 11, so therefore A to E will cost us a 21, right? Now F to G costs 12, right? And then getting from A to F is 11, so therefore that costs us 23. Also, the moment you step into F, you mark it as visited, right? So this is what we get, and we can kind of end that. Now we come to D, right? So let's look at D here. Now, what are the different edges and vertices that D can look at? D looks at quite a lot of things. D looks at B, D looks at C, D looks at G as well. It looks at all three of them. And it says also E and G, we forgot to fill this. This will be F, right? Awesome. Now, let's continue. So D. Now at a D, what happens is D says, okay, I can go to B at 11 cost, but notice B can already be reached from A at a cost of 7. So it is completely useless to even try this path out. So we ignore it. C to D. So D says that it can reach to C at a cost of 10, right? So it says that it can reach to C at a cost of 10. So try adding. So 10 plus 18 would result in 28. C can already be reached in 19. So that is a wasteful idea. So therefore this particular vertex is not even considered. CD is a trash vertex that we will not actually be using. Okay. The next vertex to consider here is DG. Okay. In fact, we should have started with this, but I kind of just wanted to show that, okay, these two are also, the other vertices are kind of bad. So DG costs us a 9, right? So if DG costs us a 9, that means that D can get us to G at an overall cost of 9 plus 18, which is 20. 9 plus 18, which is 27. Now 27 is much greater than 23 that F already does. Therefore, any of the edges that D is offering is kind of bad. So we don't care. We say that, okay, buddy, you tried your best, but you can't actually give us any good offers. So you are out of the game. Okay. Now C. Okay, so when we consider C here, so C itself is quite an interesting one. Right, again it says C to D at a 10, which again not really, it wouldn't really be accepted because it's a weird indirection kind of thing. Like, note how C costs 19 plus 10 would be 29, and 29 is much greater than 18 that D already gets from B. Therefore this edge will be ignored. C to B will also be ignored. B can already be reached at 7, so there's no use considering it. Then the next thing that C can do is that it can get you to E at a cost of 8. So C costs 19, 19 plus 8 would be at 27, right? But you can already reach E at 21, therefore we will completely ignore that as well. Now we finally are at E. E offers us a path to C at 8, but then again, 28 versus 19, sorry, 29 versus 19, clearly C already has a good path. We don't have to offer it any weird thing at all, right? So that is basically what it is. And then we have FE, which costs us 10, but you can already sort of see, F already, you can reach F at 11, sorry. So there is no use offering a path from E, which will cost 31 instead of 11, so it won't be considered at all. And then you have EG, which costs us a 7, right? So if you take EG 7 plus 21 is 28. Now 28 is much greater than 23, therefore nothing will happen. Okay, this particular path that G already has will kind of exist, and that is, I think, is about it. There is nothing else to do. Now we are finally at G, and G can get us to 3 vertices. So GD, if you consider that 9, so at a cost of 32, you can get to D when compared to 18. So clearly D wouldn't care, it will still, you would still reach it through B, basically. That's the kind of thing. And if you check for F and G, you would get 12 plus 23 would simply be 35 is not a very good cost when you can already reach F at a cost of 11, so that also will be ignored. Then you finally have EG, which costs us a 7, so 23 plus 7 is a 30 compared to 21, so E already has a very good path, therefore you will not consider it at all. And that basically is how you can use Dijkstra's algorithm to find out the shortest path from one point to all the other points in the particular system. So it's not all pair shortest path, that is not what this is. It is shortest path from one particular origin vertex, right? So we start from A, we notice essentially what we are noticing is that if we go from A, we go to B, right? And we can also go to F. Well, there is no directed edge here. F, we can get to F, right? And then from B we can get to C and E, and from F we can get to E and G. right? That is basically what the understanding is, and I think that is basically about it. A, B, C, where is D actually? Oh, this is supposed to be D. I wrote an E here, but yeah, I think that is the point. A, B, C, D, E, F, G. So yeah, so you can start here and then you can basically get anywhere. You know what the cost is of every single sort of vertex to get to a particular vertex, that is, and you also know from where you actually have to go to actually get to the vertex. That is basically how Dijkstra's algorithm works. It does not find all pair shortest path. It is a greedy algorithm that only finds the shortest path from one particular vertex to all other vertices. People usually like to call it all pair shortest path because they're generally looking at a lab program that runs n times so that it can basically find all pair shortest path, but then that becomes a different algorithm. So that is not Dijkstra's algorithm. I mean, it is algorithm, it is the Dijkstra's algorithm, but technicality, of course. So that's basically about it. It's a very simple and elegant mechanism actually. Here unfortunately the graph didn't update much. I guess I should have taken a simpler example, but well, we will see. That's about it. See ya.